Okay, so let's get started again. We've done the hard work. We've sort of laid the foundations, laid the framework for talking about cake cutting, the division of a divisible heterogeneous good. And it's time to sort of reap the benefits and sort of actually see some nice implications, see some nice development of some nice algorithmic ideas. So just to, again, like warm up our proof engines, let's start with a simple claim, and I'll need your help in actually proving this sort of claim. I'll not even call it a theorem, it's just a claim. So the first one is that NV freeness implies proportionality. Again, I'm not going to sort of keep repeating the fact that we are going to work with the setup with evaluation functions satisfy three assumptions. What were they? We had three assumptions on the evaluations, at least. No? So the evaluations are non-negative, they are divisible and additive. So if I take intervals, they just sum through it up. Like the value of two disjoint intervals was the sum of those two. So is that sort of fresh in everyone's mind, or should I sort of go back to? Yeah, so here they are. Non-negativity, divisibility and additivity, sort of the somewhat atypical one might be the divisibility, which says that if I take any interval, there's a meaningful way in the valuation terms to say half this value or 1/3 this value or lambda times this value for any lambda between 0 and 1. So that's an assumption that we'll make, and as we discussed, this sort of rules out point masses, this rules out these degenerate cases where the value sits on a specific point, the entire value lies on a diamond that's sort of been plugged into the cake. So with these three assumptions, under these assumptions, I would want to prove that for general cake cutting setup, so for any number of agents, NV freeness, that is the second solution concept, which says that everyone is satisfied with its own interval, actually implies proportionality. So this second comparative notion of fairness actually is stronger than the first one in this sense. Okay, so here comes a proof. So the first one is that like we fix an NV free allocation. So we have these intervals, the subscript tells me which agent receives it. So again, note that this I here is not really a numeral in that sense, it's just the identity of some agent. So I have say this is I7, this is I3, sounds like iPhone models, I10, why not, so on. So every agent gets one of these intervals, this partitions the whole cake, and I'm assuming that this is an NV free allocation. Note that this is sort of a leap of faith. I haven't actually proved to you that such things always exist. So that's something I'm kind of shrugging under the carpet for now. We'll get to it sooner than later. But say there is an NV free allocation. There's this partition I1 through In. These intervals are NV free, i.e. they satisfy the second property for all pairs of agents. So now the first thing I'll note is that I'll also fix an agent I, right? So pick any agent, 1 through n, up your choice, it's the identity of the agent. So first of all, note that I can write, so if I sum over all these n intervals, so I'm looking at the value of I, right? So Vi, the value of I. Now I'm looking at the value that I has for all of these intervals. So I just sum these numbers up. So Vi has some value for the first interval I7, she has some value for the second interval I3, so on and so forth. So I'm just looking at this sum. So my claim to you is that this is nothing but the value that I has for the whole cake, for the whole 0, 1 segment. Why is this true? It's a magic word I'm looking for, starts with an A. It's additive. Valuations are additive. This is a partition of the whole cake. The value of this entire union is just the sum of the values individually. And what is, by normalization, what is the right hand side? It's 1. I've normalized it to 1. Okay, so far so good. So all this says is that if I looks at the entire division, looks at the value it has for all the sort of intervals, sums it up, it comes to 1. Fine, it's additive, has to happen. Okay, so this actually holds true for any partition of the cake. I have not used NV freeness. This is just a consequence of additivity. It's just a property of the valuation function. So now I'm going to, for the first time, invoke the fact that this allocation, this n partition of in intervals is NV free. So what does this mean? This just means by the definition of NV freeness is that I have the value that I has for its own interval is at least the value that I has for any other interval. So this is for all and again let me repeat that I don't really have to be explicit about the fact that I is not equal to j. When I is equal to j is equal to I, so there's an equality. So again, this inequality holds true. Okay, so as someone had already pointed out, this is pretty much all I need. What do I do now? Can someone suggest the next step forward? It's kind of suggestive the way like I've written it in a suggestive manner, like this is right below the Vi, Ij are vertically aligned. This is true for all j's, yes indeed. Perfect, yeah. So, I mean, the single word answer is I just sum these inequalities up over all j's, right? So, I will erase this to create some. So, all I'm doing is I'm fixing an I and I'm summing this inequality across all j's. So, there are n possible j's which includes I itself, but what I'll get is n times Vi of II because the left hand side stays the same. I is always comparing with its own value is at least this I know is exactly equal to 1. It's written right here. So what does this tell me? This tells me that if I look at the value that I has, again dividing both the left hand side and the right hand side by n, which is I get this. So what does this tell me? Well, this tells me that the inequality required for a proportional fair division, required for proportionality actually holds for all I. I mean, I can repeat this argument for any I, there you go. So this essentially tells me that NV freeness is a stronger solution concept than proportionality. In particular, it tells me that if I give you an allocation that's NV free, it has to be proportional. So again, let's circle back and notice one thing. I have established it for the case where every agent receives a contiguous part of the cake, every agent receives an interval. It's a good exercise for you to say that this again holds even if the agent gets like disjoint intervals, as long as I have NV freeness across these crumbs assigned to different agents. Again, the same argument verbatim kind of holds. So this NV freeness implies proportionality even if in this sort of more general setup where I'm not forced to assign a contiguous part of the cake, where I'm not forced to assign a single interval to each agent, right? So this is sort of, yeah, think about it as you're walking back to your, well, you don't even have to that much time, just think about it as you're climbing down the stairs. Okay. So that kind of establishes the first claim. And pictorially what this means is that if I look at the space of, so if I look at the space of all, so all allocations, so how many allocations will there be if I give you a cake? Can I put a number on this? What is, like, is this a finite set? It's an infinite set. How many ways can I divide a cake into n disjoint intervals? What is that? Infinite, right? I mean, they're cuts. I can place them anywhere. So, I mean, the equivalent way of thinking, you can uniquely associate with each allocation, in some sense, a probability vector. Will bank on this sort of mapping sooner than later. But yeah, this is an infinite set. There's a lot of them. And then in this space, you have proportional ones that satisfy the first inequality that every agent gets 1 over nth. Note that, again, I have not actually proved to you that this is a non-empty set. For all we know, there might be a cake cutting instance, there might be such complicated valuations which, while satisfying the three assumptions, lead us into a scenario where I can never find a proportional allocation. So for all we know, this set might be empty, but let's just say it is not, and we'll prove that it's not. But what the previous claim tells me is that the picture looks like this. I have all allocations, some of them are fair in the sense that they're proportional, and then there's an even smaller set which are NV free. So if you're here, if you give me an allocation that's NV free, it's guaranteed to be proportional, and hence I have this sort of containment. What's non-trivial and which will take us some sort of mathematical machinery is to prove that even the innermost set here, the set NV free, they always exist. So these sets are non-empty. What we will do now, moving forward, is to actually show that this set right here, the set of proportional fair divisions, is actually non-empty, and we'll do it sort of the way we like. We'll do it constructively via an algorithm. So that's the first item on our agenda. We'll try to prove that given a cake cutting instance where the evaluations satisfy three assumptions, you will always have a proportional fair division. Okay, so before actually moving on, here's sort of a exercise. So when you have, for the special case of two agents, when n is 2, when you only have Abraham and Lot, then a proportional allocation is actually also NV free. You will again need to use the three properties. Simple exercise, think about it. I'm sure if there are questions we can sort of circle back to it, but yeah, it's kind of a simple jugglery. Okay, so this says that the converse is true. Converse of the previous claim is true for two agents. We'll see why 2 is sort of the right number. As soon as we go beyond 2, this claim actually does not hold true. We'll see an example to begin with. So So when you have more than 2 agents, I'll now give you a very specific example wherein the converse is not true, i.e. I'll give you an example where there is an allocation that's proportional, that's a proportional allocation, but it's not NV free, right? So again, this is for n more than 2, and this is for true in general. So what this says is that there are cases where you have allocations right here. The allocations that live, they are not NV free, so outside this innermost set, but they are still proportional, so contained in the sort of second level of the onion. Okay. So why can't I claim that there are instances where no proportional is NV free? Just like almost a trick question, but yeah, let me just see why that is. I'm claiming that armed with whatever we have discussed so far, the following statement is blatantly false, that there are cake cutting instances wherein if you take any proportional allocation, then that is not NV free. Yeah, I'm assuming that set of NV free allocation is not empty. Well, if that's the case, then these two would not intersect, right? But I've already told you that the innermost is always a subset of proportional, so cannot be. They always is, like, again, modulo this fact, that non-trivial fact, that NV free always exists. You just take an NV free allocation, it's guaranteed to be proportional. So that right there is an allocation that's proportional and NV free. So sort of the example I'm going to tell you is that there are some proportional allocations that live here, i.e. that are not NV free. Yeah, it's just the two solution concepts. I'm sort of hammering it in again and again before we go to algorithms, so that sort of is somewhat internalized and you're comfortable with sort of playing around with two notions of fairness. Like if there are questions, I can sort of address them, but yeah, hoping that sort of the distinction between the two is clear and sort of before we actually get to some algorithmic results. So I'll prove this sort of claim right here through a sort of example. And I'll use this example to actually specify something like, again, something that's used quite often in literature, which is So I'm saying that, look, one way to a specific way, I've assumed these three general properties, but one specific way I can specify the valuation of an agent. So this is certainly a restriction on the model, is that these valuations can come through a density function. So think of like a probability density function sitting on the interval 0, 1. So for agent I, so we have, again, this is sort of restricting the whole setup. It's like looking at a particular class of valuations, if you will. The class of valuations are the ones that are induced through a density function. So for agents, we have some density function which takes a point, every point in the interval, and spits out real number. So it's a function that just sits on, whose domain is 0, 1. So pictorially, you have the 0, 1 line. This is the density function of I. What do I mean it's the density function? It simply means that if I want to compute the value of an interval, then I just integrate the density function. So I look at the area under the curve, and that tells me the value of this interval. So value of agent I for an interval I is defined to be just the integral of this. So I just integrate over this interval, density function just spreads out. So think of it as just the probability density function. Because of normalization, this is indeed a measure. It's a probability density function, right? So in particular, the normalization tells me that if I integrate over the entire interval, this dix dx, then this has to be 1, right? The total value of 0, 1 is 1, which is exactly the left-hand side of this equality. So that's one way, that's one class of valuation functions we can look at, and so we'll say so I look at a valuation function vi, which is induced by this density function di. We'll say that this is piecewise constant if di is piecewise constant. This is just nomenclature, right? I give you a density function that's constant for some time, goes up, goes down, stays constant. It's like a pulse. Such DIs, the valuation they induce, are called piecewise constant. Standard nomenclature. I'm just throwing it out there in case you read some book or text. If this word comes up, should be familiar with it. So again, here's a concrete example. So what I'm drawing here on the y-axis is the value of di. Picture isn't great. Let me try again. Okay, this is constant up to Picasso. So say here it's 0 for some time. It's 3/4. So this is the density function. It's the value. So if I pick any point between 0 and 1/4 here, the value of the density function is 1, and say it's 0 again between 1/4 and 3/4, and now say again it's constant again between 3/4 and 1. Can someone sort of tell me what the value of the density function has to be? So I'm saying this is constant again. So what should be the value here? What's the height of this tower? 3. Anyone else? Can someone explain this to me? Right. What's the value of the interval for this agent I? What's the value of the interval 0 to 1/4? What is that? 1/4. Why is that? It's just the area under the curve, right? This is so integrate, and so the total value has to be 1. So what's the value in this right here, in this total value that I must sort of push into this? What is that? 3/4, and the sort of base is 1/4, so the height has to be 3. This is 3. The di here is 3, di here is 0. So it's just a piecewise constant function, a bunch of towers, and the way I find a value is just integrate. Okay, so with this, again, the purpose of this is to sort of again give you like some piece of nomenclature that shows up in literature. It's kind of standard enough for you to know, and more often than not, you can find good examples just working with such valuations that are induced by piecewise constant functions. Another sort of advantage of such valuations is that I can give them to you as explicitly give them to you as inputs. Note that the level of generality in which I've defined the valuation function, it's not obvious, right? Like it's a value for every interval. So I want to feed it into a computer program. How do I do it? Like again, there are infinitely many intervals. Even with the 3 properties, it's not obvious if there's a succinct way for me to actually give it as input to a particular program. In contrast, if the valuation function is piecewise constant, i.e. comes from such density functions, then I can give it as input it as an input to a particular program by just specifying these breakpoints and the heights of these. So I can give this density piecewise constant density function, input it into a program. So that's another sort of advantage of this valuation class. They can be sort of handed over to a piece of software explicitly. Okay, so now with this sort of digression, let's get back to the task at hand, and I would like to now prove or through an example, establish through an example that there are allocations that are proportional but not NV free. Okay, so here we go. So I have n agents, so n more than 2. So it's sort of overload, but I hope this is not point of confusion that I'm using both 1 through n to index the agents and to count the number of agents. It's just kind of it's a notational ease, if you will. So here's the thing. So in this example, the density functions are actually completely complementary. That is, if I look at any point in the interval, only one agent, uniquely one agent will actually have non-zero value for the density function. So what do I do? Here's a simple idea. So this is the halfway mark. The cake is lengthwise equal on the left and the right. Now I look at small intervals of length, say 1 over 2n, right? So this right here is the length of the interval, and this is, say, valued by agent 1, and the density value is exactly 2. So this is for agent 1. So what's this is only for agent 1. So D1 subscript means it's the density function of agent. So what's the value that agent 1 has for this tiny piece of cake of length 1 over 2n? What's the area under this curve? It's 1 by n. So if in particular I've designed it such that if agent 1 gets this tiny piece, proportionality is achieved. So that's pretty much what I'm doing. And again, I'll kind of repeat it. So I look at the next interval again of length 1 over 2n, and now it's agent 2's turn. So D1 kind of drops to 0 here. It's only D2 that stays at 2. And so 2 values this piece again at 1 over n. So the density is 2, the length is 1 over 2n, and multiply the 2, the area under the curve, like integrate, I get 1 over n. So these are very nice and accommodating agents, as in they don't fight with each other, they're so good friends. One likes chocolate, the other likes strawberry, just kind of separate themselves out. So this story repeats till half. So here it's dn, and again the value is 2, and the length is 1 over 2n. The choice of the length ensures that if I run over all n agents, this will actually, so far the construction will stop at 1/2. So n times 1 over 2n is half, so this is exactly why I picked this length. So note that it's quite nice and sort of good to go. So this is, if I haven't completed the valuation, let me do it now. So I have half of the length left, and for each agent I have 1 over, so just a calculation. So I have 1 minus 1 over n value left for every agent. 1 over n has been consumed. So, and kind of divide it uniformly in this range of 1 through 1/2. So I kind of double it actually. So on the left half, they are completely accommodating. On the right half, they are completely competing. Just everyone wants it, and it's just slightly below this. Note that what's the total value for any of the n agents for this right half of the cake? The length is 1/2, density is this, you multiply, you get 1 minus 1 over n, which summed up with 1 over n is exactly 1. It's a tailor-made example for satisfying all these properties. Now my claim to you is that there's an obvious allocation here which is proportional but not NV free. Can someone quickly point it out to me? So I actually want contiguity. You're right, that will work too, but agent 1 gets disconnected pieces. But here's my like proposed allocation. Agent 1 gets this, the tiny piece of 1 or 2n, designed to satisfy proportionality. Agent 2 gets this I2, so again the indexing matches, so on and so forth till agent n minus 1. And say I am the last agent, and happily I just walk away with a huge chunk in. So this is proportional. Why can someone, and even better, why is it not NV free? Who's the sort of point of NV for everyone in this example? What is that? The last agent, right? Because I mean, so if it's proportional, because if I look at VI, this is at least 1 over n. In fact, for the first n minus 1 agents, this is met with an equality. The nth agent actually gets its total value. So Vn of In is 1. I'm very happy. Almost gets the entire total values worth of cake. But everyone envies In. Right. So if you look at, for example, this is 1 over n, but when one looks at what the last agent has in store, what is this? What is that? 1 minus 1 over n. Okay. Yes, no. I mean, the density function of even agent 1 is this. So this entire piece. So here the density of agent 1 is 0, but this piece is entirely valued by it. Its total value is exactly 1 minus 1 over n. And of course, I have the property that n is strictly more than 2. So this thing right here is more than, if 1 minus 1 over n is strictly greater than 1 over n, and there you go. Everyone envies the nth agent, right? So if yes, no. Okay. All right, so that's sort of the thing, and without further ado, we're now at the cusp of talking about some algorithms and seeing sort of simultaneously and sort of in symphony, we'll sort of see some existence results for first of all the proportional division. So this is sure, yeah. So this is sort of a would someone like to give it a crack right now? So obviously I can't give the whole second half to a single agent. What can I do? I yeah. So again, if I allow like non-contiguous pieces, then so the exercise is simpler. I actually want if I want to set a higher goal for myself, I want a allocation in the sense that I want to partition it into n pieces where I achieve this. Okay. Yeah. Perfect. So you have to be slightly careful because the density here is slightly less than 2. So even if you like give me 1 over 2n, it's slightly less than 1 over n. So you can't like give the whole thing. But okay, so this is, you can do it. You just have to sort of pick your partitions a bit carefully. But it's a good exercise to sort of figure this out. I mean, yeah. Even without, I mean, I'm armed with a very generic result that NV-free allocations always exist. So I don't even have to look at it to sort of say that one will. But yeah, just think about it. You have to like be a bit careful because the density here is slightly less than 2. So the lengths have to be uh, managed accordingly. But yeah, you can sort of cut it slightly like shorter and deeper and sort of get away with it. Okay, so if so if there's interest, I can actually go over it in one of the tutorials or like offline, but I'll leave it here. Sounds good? Okay, so finally, this is too much of a delay for a computer science audience for an algorithm to show up. So again, I think. And of course, we'll start with proportionality and the sort of message, the punchline being proportionality is much better, much more of a tractable solution concept than NV freeness. In particular, here's the theorem that will prove it's an important enough result to deserve the status of a theorem. It says that again, I'm not specifying that I'm looking at a k-cutting instance with general n number of agents where the valuation satisfies the properties that I have been like boring you with for the past 1 hour. And here's the cherry on top of the cake is that not only do such fair divisions exist, proportional divisions exist, they can be computed efficiently. I have to be a bit specific about the computational model, but yeah, let's for the time being say the valuations are given as explicit input through these piecewise constant density functions. So if it's a general result, but if it kind of eases you, we are, for the time being, let's say the valuations are piecewise constant, right? So given those valuations as input in polynomial time, you can always find a proportional division and allocation that satisfies proportionality. This in and of itself proves that as a fairness concept, proportionality always exists. So it's not only an algorithmic result, it's an existential result wrapped into an algorithm. Okay, so what good is a theorem if you don't know at least 3 proofs of it? But for the time being, we'll look at 2. And we'll prove it via 2 methods. First one is called the moving knife procedure. This is due to Tubbins. And the second one we'll prove is through the even paths procedure, protocol, algorithm. So indeed, they're classic results, almost 4 decades old, and it's probably a good time to sort of so there's a chapter on cake cutting methods by Ariel Procaccia. So sort of that's a good reference, particular at least the two procedures that we'll discuss now can be found there. So if you want to read up, it's a good textbook to sort of look at for computational social choice in general, but in particular for cake cutting cake cutting algorithms that we'll discuss. So again, before I actually get to this moving knife procedure, let me re-emphasize that it guarantees a proportional allocation for any number of agents. It's not just 2, it's for n. For 2, we have already seen the cut and choose actually works. It works even better because it gives me an NB-free allocation. So let me write down the pseudocode for it, and then we'll sort of discuss why it works and why it's called the moving knife procedure. So yeah, so at least for the first few algorithms, I'll be like very pedantic. I'll like explicitly write the pseudocode every step. It will sort of help us internalize things. Going forward, if this is too simple, I'll just discuss the highlights of the algorithm and kind of skip over the mundane, like small little details. But at least for the first few algorithms, it's like write it explicitly, almost in form that you can, if you want, you can code it up, so on and so forth. So what I'll do is initialize this number, say some parameter to be 0. So this is like a left cut mark, if you will. And U is sort of or let me call it W, it's just a set of waiting agents. So this is the set of agents that still haven't received an interval. They are still looking to get an interval assigned to them. So let's for now say the valuations are piecewise constant, so given as explicit input, but I'll get to a model where this can be sort of made black box. Yeah, it's a good point. Right. So I'll initialize this mark, say L, to be 0, at the leftmost edge of my cake, and then I have assigned the set of weighting agents is just everyone is weighting, no one has been given a piece, L is 0. Right, so now what happens is that I iterate and so while I have more than one agent waiting, so I have 2 or more agents that are still that still haven't received a piece, that still haven't been assigned any part of the cake. What I'll do is like loop and so I'll ask every agent who's waiting to tell me a mark such. Okay, so this is sort of the most intricate part of the algorithm, if you want to call it that. So what I do is quite simple. I look at every agent that's still in waiting, that's still in the queue, and I'll ask the agent, okay, here's a left mark which I'll keep updating, but now start moving a knife from this point L, hence the name moving knife, and I'll ask the agent to stop as soon as it gets to a point where the value is equal to the proportional share. So as the algorithm proceeds, L will be somewhere here, and for every agent I'll say, okay, you move a knife and stop at xi such that the value that, let's say xa, sorry, and let me stick to I since I've been forcing I upon you. So I start at L, which is my updated mark. I'll ask the agent, okay, you tell me a point, the first point, the leftmost point, where you reach an interval of value equal to 1 over n. So V for this particular interval is exactly equal to 1 over n. Right, so I'm asking the agent, okay, move the knife and stop it when you have achieved proportional value. Okay, so at the first iteration when L is equal to 0, obviously you'll have many marks, some will be to the left, some will be to the right, and at this point what's a natural thing to do? Is the algorithm clear so far? So who should I give it to if you had to make a guess? So what I've done, let's look at iteration 0. So L is equal to 0. Everyone puts a mark. So this is the first iteration. This is my cake. So agent 7 says, okay, if you give me this much, 0 to x7, I'll get 1 over n, kind of happy. Agent 6 says, okay, I'm here. Agent 2 says, no, no, look, I'm very calorie conscious, even just this much will give me 1 over n, and so on. So everyone makes such a cut, x1, xi. So what is a smart thing to do here? What is that? Yeah, just give it to the leftmost, right? And you'll sort of intuitive, look, this is the guy who gets happiest the earliest, wants the smallest piece in some sense with respect to the current left marking L. I'll just give it to this guy and see what happens. So I'll pick I star, which again is, yeah, so what does argmin mean? What does the min operator mean? So Agmin means I look at this set, I look at all agents who are still waiting, still in the set W, and among them I pick the one with the smallest xi. Right. So again, it's a very intuitive thing. One way to interpret, which is not this algorithm, is I start at L, keep slowly and continuously moving the knife. As soon as someone shouts stop, i.e. someone says I've reached this, the piece now to the left of the knife is of value 1 over n to me, I cut the cake here. So again, at 0 I'll keep moving from here. X2 will be the first person to shout, okay, I've got 1 over n, boom, the cake is cut, the process repeats, right? So now I'll update L to be xi star, right? So this goes to I. So in particular, this means that I star is out of contention. I have assigned right, this was the mark specified by I star. So in this example, it will be x2, 0 to x2. That's the interval that's given to the second agent. So I cut this cake. I now am left mark is here. I'll only work to the right of it. This interval goes to I star, and I star is happy, is out of the waiting set. Yeah, no tatkal required. Boom, boom, boom. I keep iterating. Right. So again, if two of them shout at the same time, if then I break ties arbitrarily. For example, I can just give it to the smallest index. So say I'm moving it and both of them say, okay, stop here, doesn't matter. I give it to exactly one of them. The other one still continues to be in the waiting set. Right. So when will it happen that bunch of agents keep shouting together? Can you give me an example where this happens? The case that the cut happens, the cut coincides all the time. What if the valuations are identical? No, then what will happen? Okay, let's see if we understand. So say I'm a special case where all the valuations are identical for all the agents. Like Vi is equal to Vj for all Ij. Certainly not a very interesting case, but say if I have that and I run this algorithm, what will happen? What is that? Exactly, everyone will shout at the same time, right? When you move the knife, the value of 1 over n is achieved exactly at the same point for everyone, right? It's the identical valuation. So all marks, all the xi's will actually, here will coincide every time. So you'll pick one of them arbitrarily, assign it, move on. In that case, do I get a proportional allocation? Is that obvious? It's not too. Okay, let's very special case, very simple case, before actually we jump on to more general constructs. Say I'm in a world where in a cake cutting scenario where everyone has the same valuation, right? What will end up happening is that when I move the knife, when I execute this algorithm, this xi will always be the same for every agent, right? Like wherever you are, if this is of value, say you're here L, there's some number of agents left. If for some agent xi, this interval is of value 1 over n, the fact that the valuations are identical means that this interval is again of value 1 over n for everyone else in W. So the xi's always coincide, right? But now notice that what's happening is that the first agent that goes away gets a value of 1 over n. That's by design. I star is kind of happy because this interval was exactly of value 1 over n to I star. That's why I star shouted. But you are always removing a value of 1 over n, 1 over n, 1 over n. So in fact, everyone else ends up getting 1 over n. There are n agents. All of them get 1 over n. They have identical valuations. The valuations are additive and normalized. There you go. Right. So if that's not clear, let's go over it one more time. If it is, I'll try to move to a general proof. Yes. No, we are following the algorithm that's written in black and blue, white and blue here, which is that I start off with so think of it as like a mediator implementing it in contrast to cut and choose, but whatever. So the idea here is that I start with L equal to 0 and I'll keep moving. So again, this algorithm is quite explicit. So all I'm saying is, let's just read it as a pseudocode. For every iteration, I'll ask each agent to give me this xi, right? And I'll pick the one that is the leftmost. So argmin here, this is the leftmost mark. If argmin is sort of confusing in particular, so I've run the algorithm, I have some value of L was 0, but now like I look at all the guys that are in W, everyone tells me like xi is here, xj is here, xk is here for different agents. I'll pick the one that has the leftmost mark, say k, and k gets this interval. The fact that this is of value 1 over n to k is by design, and this is right here. And so this agent is happy, right? And then I give this to ik, I push k out of the waiting list because it has already received the interval, and I update L to here and I repeat. So there's no cut and choose per se, it's just cut and assign. Okay, move your knife, assign, boom, boom, boom. My claim to you is that this simple case where all the valuations are identical, you are good to go in the sense that everyone will get exactly interval of value 1 over n. Because when the first time everyone shouts like x1, x2, x3, xn will be some identical, you give it to x1, right? You have moved one agent out, but the remaining cake is of value 1 minus 1 over n, so on and so forth. Right? So if the valuations are identical, it's sort of the execution of the algorithm is sort of simple to follow and so gives you proportional cake division. What I'll do next is sort of argue that this is actually true in general. Even when you have distinct valuations, this algorithm ends up assigning a proportional allocation. And let me just complete it by saying that yeah, there's no other one. It has to be exactly that. Yeah. So the question was, if the valuations are identical, how many proportional allocations are there? Well, n factorial. Right? You can assign one and permute it. Like the permutation won't change. In fact, that's exactly the NV free ones as well there. So what's not obvious about it? Like what is the sort of trick? Like what's the subtlety in arguing that this thing always finds a proportional allocation? What's the, like, what essentially do we have to argue to sort of show this proof actually works? What is that? Yeah, I mean, among other things, at the last, in fact, I mean, it does run to completion. That's one aspect. I mean, what's not obvious right now is that we don't end up in a scenario where the cake that is left is of value less than 1 over n for all the agents in W. Right? It's not the case that you have actually over-assigned things. And this is exactly where the selection rule comes in. I'll write down a proof just to be specific, but the argument is really pedestrian. All it's saying is that, look, every time you are keeping me in the waiting list and assigning it to someone else, with respect to my value, you are not giving away more than 1 over n. Right? Why? Because whoever remains, the xi's were greater than equal to xk. Right? So for these guys that did not get a piece, these guys who were still kept waiting, this chunk was not of value at most 1 over n. Right? So you moved away one agent, you gave away something that was of value less than equal to 1 over n to me. Again, you gave another piece to some other agent, but again, this was of value less than equal to 1 over n to me. So overall, it will never be the case that you have sort of given, if the k agents removed, the value that has been lost is sort of not high enough, and which essentially means it's not more than k over n, and whatever remains is sufficient to argue that this algorithm will run to completion. In particular, it's sufficient to argue that the last guy, the chunk of the cake that remains, is of value at least 1 over n. I'll do it specifically, but I just want to sort of ease into the fact that really the argument isn't something, there's no fancy math, it's a high school, if not less, level argument. It's a very fairly, once you have the algorithm, the argument is quite clean, quite simple. And again, something for your notebooks, whenever you have an existence result, try to pinpoint where does this existence argument, what's the root of it. And here the root is a potential argument. Right? It's a potential which is saying, okay, you're removing one agent, you're removing part of the cake, but the value that remains for any agent for the remainder of the cake is high enough. Right? So it's a sort of, in that sense, the underlying, the totality here, the existence argument here comes from a potential argument. So again, let me prove it a bit rigorously, but yeah, if you understand this claim that if I kick out one agent, whoever remains, the value lost is less than 1 over n, so you are good to go. So here's sort of the So whenever you have this kind of a thing that, okay, some good properties continues to hold, I mean, your friend is induction, right? I mean, you just argue inductively that this holds. Again, this is more for the sake of doing things properly. If you understood the previous discussion, it's just sort of pretty much just making that observation rigorous. So I kind of run the algorithm and I have this iteration count k, which is the number of agents that have received a piece, received an interval, so far, right? So you're running it, you give it to 1, give it to 2, so on. So the k is this iteration count that keeps on growing. So if here, what will be the cardinality of set W? How many agents will be waiting? If I, okay, let's see. I'm running this algorithm. At some point I stop it at the end of the while loop. At that point of time, I have assigned pieces, intervals to k agents. How many agents remain? N minus k. Right, so, right, I've given it to k. Whoever I've assigned, I kick it out of W, right? That's the sort of algorithm. I mean, if there was space, I would have written it here, but I hope the algorithm is sort of simple enough to, like, you can refer back to your notes, but whenever I assigned, I kick it out, so this is exactly n minus k. This is an observation, but the invariant that I'm going to argue holds inductively is that, so say this happens, so what is k at the beginning? What's the base case of this induction? 0, right? No one has received anything. But the claim is that so for all agents in the wait list, in the set capital W, if I look at the value that agent A has for the leftover thing, so again, L is the cut point at the, when I stop this algorithm while it's running. My claim is that this is at least what? So note that k is never going to be more than n minus 1, right? This essentially means that when k becomes n minus 1, the loop sort of terminates, I go out of it. So k is n minus 1, which essentially means that this thing, the right hand side here, is always more than 1 over n. Right, is plugging it in. So again, this is sort of just restating the observation we've made in a bit more rigorously. So when one agent gets assigned an interval, k is 1, whoever remains in this set W, the value of the cake, the remainder cake, which is this thing, I update L, is 1 minus 1 over n. It's still quite large. Right, when two agents go away, it's 1 minus 2 over n. It continues to be large enough till all the n minus 1 agents. In particular, when the loop terminates, there's exactly one agent left, i.e. W, the cardinality of W is exactly 1. K is equal to n minus 1. Note that this holds, the second part, this holds with equality. So even for the last agent, whatever remains, right, this last agent here is, if I prove this claim, what I have is that even for the last agent, the part that it receives is sufficiently large. It's 1 over n. Okay. What is that? L is the current, yeah. So, I mean, say like I1, I2, again, this indexing is sort of is slightly overloading, abusing notation. It's not necessary that the agents will get the piece in this order, but whichever k agents got a piece, let me just call them I1 through Ik. So these things are gone, right? Like in particular, like I1 was here, I2 was the second agent, and now IK, so say was this. So L is right now here, so this thing is exactly equal to VA of, I look at the whole interval, but now this entire chunk has been sort of assigned away, it's gone. So I remove these intervals, whatever remains, this is the part that still is unassigned. This part for an agent A that's still waiting is large enough. I'm claiming that this is continues to be 1 over n. It's actually sometimes better to prove a slightly stronger inequality. It helps in induction. So I essentially want this thing, but I'll prove a stronger one because, again, it sort of helps in, this is sort of a common phenomenon in induction that you need to sometimes have the right inequality to induct over. This is a very simple instantiation of that observation. But note that once I have this, I'm good to go. This proves that the algorithm will succeed, will successfully find a proportional allocation. Okay, so can someone quickly tell me why this is? So base case is fine, k is 0, w is all of n, and then this just says that your total value is equal to 1, so it's at least 1. So base case is golden. What's the inductive argument? So assuming it for k, can you argue it for k plus 1? So exactly where the selection rule comes into place is exactly where I use the fact that the cut is made at I assign it to the leftmost guy. So what nice property of the valuation do I use here? Yeah, so it implicitly uses the fact that the valuations are monotone. So if you are giving so for all A and W, so I look at all agents, this was the current value of L, this was XA, and this is XI star. So I star is the agent that receives an interval in the current iteration. This is the K plus 1th agent, if you will. So this interval goes away, right? But note that for A, this is of value 1 over n. So by monotonicity, which is a consequence of the additivity and the non-negative property that we have assumed, this thing, the thing that you kind of remove, is of value less than equal to 1 over n, right? So for these guys, VA of LXI star is less than equal to 1 over n. Hence, by induction, this kind of continues to hold. L was here, now you update it to here, but so what you do is like VA of, so say the new L, this thing that I'm subtracting out is of value less than equal to 1 over n by selection rule. So this is greater than equal to, so this again by inductive hypothesis I know that this is k by n, this I know is at most, it's a negative sign, so be careful, but again this gives me what I want, so sort of continues to hold. Again, it sort of looks a bit messy, but I mean, the idea is quite simple. I'm just checking off a piece of that was, I mean, you didn't claim it, which means this was a value at most 1 over n to you. Fine, then wait, one agent has dropped. You still have enough opportunities in the remaining case to sort of get a proportional share. Okay, so few observations. First one is that note that if an agent honestly follows this algorithm, that then it will receive a piece of value at least 1 over n, right? So as long as you are being honest about your marks, the cuts, you're guaranteed to receive a interval of value at least 1 over n, irrespective of what others do. Furthermore, if your input is like a piecewise constant valuation function with rational breakpoints, then you can argue that the output of the algorithm, these cut points, will also be rational. So this proves that for a rational input, by which I mean an input where the valuations are induced by density functions that have rational breakpoints, there exists a proportional division. Not just that, there exists one where the breakpoints are rational. So this, again, two sort of observations. Again, sort of you can offline go over them and verify that these two facts are correct. Okay, excellent. So what we have done is actually managed to prove that there's an efficient process. In particular, if I give the valuations as explicit input, say the densities as explicit input that induce these valuations, so polytime algorithm, right? My question to you is that say I work in a model where I actually do this thing in a query-like setup. So at every time, in every iteration, when I interpret this step as literally asking the agent to tell me what xi is, right? So I go to this, for every agent I ask this. So now with this sort of query interpretation, where you have n agents sitting in the room, I'll ask everyone mark, and I'll find the leftmost mark, give it to the first agent and say, okay, you're done, walk out of the room, iterate it, and someone tell me how many queries I'll make. What's the query count of this moving knife procedure? What is that? N into? Yeah, it's theta n square. Right? Yeah. So why is this? Well, you just look at the cardinalities of W, it's decreasing by 1, and every time you run it, you actually ask every agent in W to sort of tell its mark, right? So initially, so you ask n queries in the first round, n minus 1 queries, that's the size of the wait list, the set of agents that still haven't been assigned a interval, yada yada yada, to 1, which is exactly theta n square. So that's the sort of number of efficient but quadratic. Okay, like a good computer scientist, the question is this the best we can do? Can we push the envelope a bit more? So note that if the valuations are piecewise constant, that is, if I have density functions, then I can give them as explicit input. But if I sort of step back a bit and only look at valuations that satisfy the 3 properties I need, then it's not obvious if there's a specific model wherein I can give them as explicit input. Right? These are defined for infinitely many intervals. So even with additive evaluation, it's not obvious whether I can give it to you, give this as an input. So sort of the right complexity model to study cake cutting algorithms to sort of identify the efficiency for a bit more general valuation class is to in fact look at the query count. And this is a very natural measure when you are interacting with agents. Right? You have n people, you want to divide something fairly among them. It's kind of natural to ask them for their valuations as you successively make allocative decisions. So this query count is a natural measure, and it's sort of formalized in this model called the Robertson-Webb model, again proposed not surprisingly by Robertson-Webb. So again, the point is that there might not be a finite discrete representation of a cake cutting problem instance, and this is the concrete complexity model we sort of adopt to specify the number of operations required in a cake cutting algorithm. It's a query complexity model. So the model has two very natural, so how do you interact with the valuations? Well, think of it as you have n agents and their values are somehow specified as a black box, and you can query every agent about its value. How can you query them? There are two types of queries. The first one is simply an evaluation query. So idea is you ask an agent A, okay, here's an interval, the left point of this interval is x, the right point of this interval is y, what's your value for it? So it just looks at 0, 1, xy, you query the agent replies with a number, the number is exactly this value, right? Its value for this interval xy. The second type again is of the form x alpha, and this sort of now returns a mark z, a point z. So you have a target value alpha in mind, and you ask the agent, okay, if I start at x, and if you want to achieve a value of alpha, where should I cut it? So this is the target value alpha, and VA should achieve this target value within this interval. If there is no such mark, say agent returns like a null or some standard convention. So my claim to you, okay, which kind of a query will I need to run my moving knife procedure among these two? What is that? The second one, right? So I'll call the second query with what value of alpha? With what value of x and with what value of alpha? What is that? -2. Huh? I the answer was I would run the second one. What's the, if I want to run this algorithm with this query model, what is the value of x and what is the value of alpha? It's a very trivial question. X is L and perfect, yeah, very simply. I just want to know exactly the value of 1 over n. The mark, finding this mark is calling this second query with x as L, the current value, and alpha as 1 over n. So the point is that if I work in this specific Robertson Webb query model, I'll need order n square, theta n square number of cut queries to actually execute this algorithm. And the sort of the follow-up question is, can we do better? Right, and when you have the first follow-up question, the answer is typically yes, and here it is. So this is the algorithm by even in paths. I will try to quickly cover this and then we'll break for lunch. But okay. So it's a recursive method, and so what we'll do here is sort of assume that the total number of agents, the number of agents for whom I want to find a proportional division, is a power of k, is a power of 2. I'm just doing this for ease of presentation. None of the arguments are like critically based on this assumption. Okay, so as I said, this is a recursive process, and the idea is uh, each successive call to this algorithm, I'll actually I'll invoke each recursive call with an interval xy and some set of agents that, again, W in the sense that these are the set of agents that would want to receive a piece in this interval. So I have 0, 1, I'll invoke this recursive call with an interval and some set of agents W who are in the end going to receive an interval which is sort of contained uh, in this scenario, right? So what's the recursive call? Well, if there's exactly one guy contesting for it, you do something very obvious. You just assign um, so if there's just one agent contesting, you just give the whole interval to this guy. Otherwise, you just again recurse and recurse in the following manner. So what you'll do is like for every agent that's contesting, that's still in this weighting set capital W, you ask for a mark ZA such that this subinterval x to ZA is of value half of the total value of the interval. So this guy just does in some sense what Abraham was doing, boom, marks a point, and you do it for every agent, right? So how many, like if I look at the query model, how many queries do I need to execute this specific recursion call? What do I need if I look at this query model? I have access to these two queries for every agent. How many times? So okay, for one specific agent A in this set capital W, how do I find this ZA in that if I have access to those two queries? What is that? For one specific agent, let's just start. I have one specific agent A. I want to find ZA. How many queries do I need? Queries of the two form that I have specified. Okay, yeah. 2, would that work? So first of all, I need to find this value, VA of xy, right? That's one eval query, right? Literally I'll invoke eval for agent A and xy. Now I know this value VA of xy, I have it, that gives me alpha, and then I invoke this cut query with that x and half the value. So I'll need 2 queries for every agent. So how many total? If the size of W is 10, I'll need 20 queries. I'll need 2 times W queries to sort of execute this step so far. Okay, and now how do I recurse? So okay, the idea is I have xy that W many agents contesting for it. Everyone gives me a mark. So this is ZA, ZB, so on and so forth. And what I'll do is I'll keep looking at these marks and find a one Z star such that half of the agents have marked, their mark is on the left of Z star, and for the other half the agents have marks here, and the other half of the agents, the marks are here. So I just sort these Z's that I have obtained for all the agents in the set capital W, sort them left to right and pick the n by 2th mark, right? So I keep going till pick the W by 2th mark. Since n is a power of 2, I can always that's why I assumed it's a power of 2. I'll always have exactly a unique median. Okay, so with this I recurse on. Yeah, those tie-breaking rules I'll not specify. I mean, if you have this, if you have the question of how do I tie-break, you should have also figured out the answer of how do I do that. It's always arbitrary. Like it's hard for me to come up with an example where some non-trivial tie-breaking rule is required. at least for these lectures. Right. Right. So if you have identical marks, you do an arbitrary partition. You just pick, uh, again, you pick W by 2 of these agents and call the recursion on the left and remaining on the right. So this is the median mark. So W by 2, half of the agents contesting have the marks left of Z star. There's some agent that is at Z star, but the other ones are to the left of it. So you recurse on this. So just call this with X Z star and those subset of W that of cardinality half that sort of made these marks. And also you recurse on Z star Y. So you kind of recurse here and recurse here. I'm not being too sort of, I hope what the meaning of left half of agents and right half of agents is clear. It's just agent ZA, whose Z is less, goes in the left half. If ZC is here, the mark is to the right, the agent goes to the right. Okay, so yeah, so if I look at the recursion tree, so at the root of the recursion tree, I have the whole interval, and W is just all of the agents. When I instantiate the algorithm, I just give the entire cake and all the agents are contesting for it. What ends up happening is that like there's some Z star that gets invoked for the first time. Half of the agents come here. The other half of the agents, the Z mark was on the right. So on and so forth. Note that what this essentially means, so this is again, and this will kind of keep recursing. So whenever I draw this line, I mean some interval. So this will be like Z star comma, like Z star 1, so to say, so let's say Z0. So just kind of recursion keeps on. What's the depth of this recursion tree? Yeah, so this is the number of agents that are competing. Here there are n agents competing. When I split it by construction, half of the agents get called with the left half, half of them. So this is the number of agents competing. Here it's n by 4. What's the depth of such a tree? Log n. Right, every time it gets halved. Okay, so the key observation here is that whenever, again, inductively, and this is maintained throughout the recursive calls, so if I'm looking at depth k and I look at an interval that has been called, how many agents are competing for it? So this is depth 1, this is depth 2, so depth 0, the root, say following standard convention. So what's the, if I look at like depth k and I have an interval here, so how many agents are sort of contesting for that single piece in a recursive call? Right, so it's again like trivial exercise to argue that this kind of drops by a factor of 2, right? You're halving it, so it's n over 2 to the k. Quite like if you want to do it, just do it. Base case induction, and the sort of another property that holds is that like for each agent, So again, base case is quite simple. When k is 0, this interval xy that's been called is the entire cake. So your value is 1, plug in k equals 0, this holds. Now every time, like if you have xy, if you look at one particular recursive call, this is z star. So if you are an agent that sort of you made a mark here, that's why you kind of, like ZA was here, which means that the value of this piece is at least the value of XZA, right? So you are an agent on the left, which means that if I look at XZA, this was half of your value for the whole thing. That's exactly how ZA, this cut was defined, right? You ask the agent to do this Abraham's cut, half and half. But note that since ZA is to the left, this whole thing is actually greater than equal to, again, monotonicity. So again, by induction, this inductive hypothesis was 1 over 2 to the k, multiply out a half, so you get 1 over 2 to the k plus 1. So yeah, this again holds inductively. And finally, I mean, when you have to log in, what you get is a single agent, courtesy this equation, plug in k equal log n, 2 to the log n is n, you have one agent, and the value that you have for this piece following from here is at least 1 over 2 to the log n, which is 1 over n. So at the root of this recursion tree, everyone gets a value of 1 over n. Okay, so let me just actually argue to you that the query count is quite less. So we have already discussed that whenever I do this recursion, I have the cardinality of W is 2 times the cardinality of W. So here the W is of size n by 2, it's of size n by 2. Here the W's are of size n by 4. So if I sum the W's up across any level, right, the size is always n, right? Every agent gets asked 2 queries irrespective of the depth of the recursion tree. So it's 2n. So pick any depth, the agent is somewhere in the recursive call, and 2 queries are being asked to every agent. So the total number of queries is 2n, since the depth of this recursion tree is exactly log n, the total sort of query count, the number of cut and eval queries that you'll ask throughout the algorithm is 2 to the n log n, which is sort of notably better than n square. There you go, you have an algorithm with n to the log n query complexity. Okay.